Hello. Today we are going to look at the limits of sequences and series as n tends to infinity. So n is the term in our sequence or in our series, and I have a particular term n here. My nth term is going to be n minus 3 all over n squared plus 2. And I want to know what happens to this expression, what happens to Tn as n tends to infinity. So we haven't done maths particularly like this before, but we are actually going to do this again in more detail when we come to something called calculus later on in our work in maths. So we're going to start off with this value for Tn, and what I've done is find the first term and the second term. So my first term in my sequence is minus 2 over 3. My second term in my sequence would be minus a sixth. So I have my first term and my second term, and then I decided I was going to do the 100th term. So we have our terms in between that I've just put dot, dot, dot for. So this is our sequence. This is n is 1, n is 2, n is 100. And can we see a general tendency in the sequence that we are looking at? We start at minus 2/3, then minus a sixth, and by t100, t of n is equal to 100, we are at 9 by 10 to the minus 3, so 9 divided by 1,000. We can see that we're getting closer and closer to 0 is the key pattern that we need to recognize. So as n is getting bigger and bigger, our Tn is getting closer and closer to 0. Now that's going to be important for the series of this as well, and we're going to talk about that in a moment. But for right now, I'm going to show you what you would actually do if you were given a question like this about limits in an exam. So you'll be asked for the limit of a function, the limit of Tn in this case, as n tends to infinity, of n minus 3 all over n squared plus 2. Now, I've given you an argument that we can see that these numbers are getting smaller, closer and closer to 0. But the way that we show this definitively, to show exactly what value this Tn tends towards as n gets bigger and bigger, what number does it get closer and closer to as n gets bigger and bigger? What we're going to do is find the largest value of n, the largest power of n, I should say, which is n squared, and we're going to divide every number here by n squared, above and below our line. So what we're going to do is divide above and below by n squared, and we have to keep rewriting this limit business each time to remind us of what we're doing, and it's just required for the exam. So we divide every term by the highest power of n involved in Tn. So divide the n by n squared, divide the minus 3 by n squared, divide the n squared by n squared, and divide the 2 by n squared. Everything gets divided by n squared. Simplify that down. N tends to infinity, we end up with 1 all over n minus 3 all over n squared all over 1 plus 2 all over n squared, and that's our job done. Now we want to let n tend to infinity. So what's going to happen to these numbers that have n or n squared underneath the line? We're going to be dividing by bigger and bigger numbers. So what happens when we divide, when the denominator of a fraction gets bigger? The number overall gets smaller. So if n was 10, we'd have a tenth and 3 over 100 here. If n was an even bigger number, or we would end up with tiny, tiny fractions that would get closer and closer to 0. So this is going to end up becoming closer and closer to 0 as n tends to infinity. So we don't just sub in n for n is infinity in here. We say, what is this going to do as n gets larger and larger as it tends towards or gets closer to infinity? So what we say then, when we apply the limit, we end up with this being 0 minus 0 all over 1. It's just a constant. There's no n involved here. Plus 0. So we end up with 0 over 1, which is what we kind of expect based on our argument at the beginning. These terms, Tn, is getting closer and closer to 0 as n gets bigger and bigger and bigger. So in the limit, when n tends to infinity, our Tn would be 0. Now, what implication does this have for S of n? The sum of all of our terms. Remember that S of n is the sum, and R is 1. In this case, we say up to n of Tr. If we let that go to infinity, if we got the sum to infinity, would be the sum from R is equal to 1 up to infinity of Tr. So our n is infinity. If we let our series just keep going on and on and on, as we got higher up in our list, adding on these tiny, tiny numbers would have very little effect on the overall value of S of n. Remember, S of n is the sum of all of our values, all of our terms. We start off with fairly big numbers, 2/3 and a sixth, or minus 2/3 and minus a sixth. But as we go on, the values of t are going to get smaller and smaller and smaller. And they're going to matter less and less and less to the overall value of the sum. So the consequence of having a limit where the terms tend to 0 is that the sum to infinity is some number. It is actually equal to a constant. So we keep adding things up infinitely, but we actually end up with a constant. We end up with a number. And that happens when our nth term, our Tn, tends to 0 as n gets bigger and bigger and bigger, as n tends towards infinity. So if we have a series that gets smaller over time down towards 0, specifically if we have Tn getting smaller and smaller down towards 0, then our sum to infinity actually adds up to a constant. It adds up to just a number, because as we get into really large values of n, they stop really mattering. They end up being basically 0, and we don't care about them anymore, and we end up with the sum of an infinite number of terms actually being just some number, which we call a constant. Again, if this idea doesn't make perfect sense to you yet, don't worry, we will come back to the idea of series and infinite series at another stage in the course. But we are going to use this basic idea in the next section, so that's why I'm trying to give you an argument for it. Now, the other two examples I'm going to do with you are just showing you how you would deal with a limit type question, and we're just going to go through them fairly briskly. So I'm going to write them down for you. So for both of these, I'm just going to show you how it is you would tackle the problems in an exam setting, and then we're going to talk about the result that we get briefly. So we have the limit as n tends to infinity of this value of Tn. So this is a Tn again, though it doesn't technically have to be. What are we going to do? We're going to divide every term by the highest power of n. What is the highest power of n in this case? It's n cubed. So every term gets divided by n cubed. 2n cubed all over n cubed, all divided by n cubed all over n cubed, plus 1 all over n cubed. Simplify that down. We have the limit as n tends to infinity of 2 all over 1 plus 1 all over n cubed. And when we let n tend to infinity, let n get as big as we like, this is going to get really, really small down to pretty much 0. So we just end up with 2 all over 1 plus 0 is equal to 2. So what does that mean in practice? It means that if we got n of 100 or n of 1,000, set n equal to 1,000 or 100, we'd end up with a number that's really, really close to 2. As n gets really, really big, this fraction ends up pretty much equaling 2. So what would this, what effect would this have on S of n? It would mean that we keep adding 2 on for each term in S of n, so it would tend to infinity. So in this case, as n tends to infinity, S of n would tend to infinity as well, because we keep adding on 2 each time we increase the e-value of n. So n just tends to infinity, but S of n, I should say, just tends to infinity. But Tn, this is Tn, or as n tends towards infinity, this is Tn. This ends up just converging, we say, to 2, in the same way as this converged to 0. So again, the method is very straightforward. You just divide above and below by the highest power of n, and then let all of your fractions tend to 0, and then see what kind of number you end up with. If you end up with 0, it means that your terms in your sequence are all tending down towards 0. If you end up with a number like 2, it means that as n gets very large, all of your Tn's are going to end up getting closer and closer to 2. But this would have a sum that would tend to infinity, because we keep adding on a big number like 2. It doesn't tend on down to 0, so we don't end up with a constant sum to infinity. Now, finally, we are going to do the same thing here. So we have the limit as n tends to infinity, and we know what we're going to do. We're going to divide above and below by the highest power of n. So n squared all over n squared plus 1 all over n squared. N all over n squared minus 2 all over n squared is equal to the limit n to infinity of 1 plus 1 all over n squared all over 1 all over n minus 2 all over n squared. And can we see what the problem is going to be? If we run the limit now, we end up with 1, sorry, no bracket there, we end up with 1 plus 0 all over 0 minus 0, which is equal to, we're not sure. You could say that it would end up being equal, or it would end up tending towards infinity, but effectively we say that the limit does not exist, because we end up with this tending towards infinity, so we say the limit does not exist. And that's all we really have to be able to say about this. So these are our 3 different important situations. We could end up with a sequence or a series where our terms get closer and closer to 0. The net effect of that is that we're going to end up with a sum to infinity that goes to a constant that ends up equaling a constant number. Or we could end up with the sequence itself tending towards a constant number like 2, which means that if we get t of 1,000 or t of 10,000, we end up with both of those terms being very, very close to 2. Or we could end up with the limit not existing at all, because our Tn just keeps growing to infinity. And that's what we need to know for limits of our terms tending to infinity, and we will deal with these in a little bit more detail at a later time in the course.